Hello, everyone. Today at Rocscience, we are so pleased to introduce our new software, EX3. To start, on behalf of Rocscience, I hope that everyone is being safe and healthy at this critical time in regards of COVID-19. I'm Sina Malami, geomechanics specialist at Rocscience and the developer of EX3's engine. In this presentation, my colleague Owen Westland, who is in charge of UI of the software, will help me, and we hope you enjoy your presentation. Also, during the presentation, if you have any question, please feel free to ask by typing them. We are more than happy to answer them throughout the presentation. As you know, Rocscience, with more than 20 years of experience, is the world leader in developing 2D and 3D software in mining and geotechnical engineering. Our products have been used by more than 8,000 users all around the world. In this picture, you can see our head office located in Toronto. Currently, we are having more than 50 employees, that half of them are having master's degrees and PhD. Here is the agenda of the webinar. I will tell you a brief history of EX3 and why we decided to launch this product. Then I will briefly talk about boundary element method, the numerical method that is used in the engine. And then I will walk you through the features we designed for the software. At the end, Owen and I, in live demos, will show you how to import geometries into EX3 if you have different formats such as DXF, DWG, OBG, or even if you have the files in different software such as Examine3D or Map3D. If you want to know why we decided to release EX3, we need to go back to the 90s. A research group in University of Toronto devoted a lot of effort in developing numerical method in geomechanics. This research team that later on established Rocscience realized the lack of 3D analysis softwares in mining industry. So in early 90s, company developed an advanced numerical package using direct boundary element method to analyze 3D underground excavation. They put a lot of effort in visualization algorithm, and finally at 1993, Rocscience released its first 3D product called Examine3D. Back then, it was a very advanced software. You could import geometries, you could discretize it in the software, and even rotate it, which was very novel back then. But between 93 to 99, company did a lot of research and development in the boundary element methods, such as enhanced displacement discontinuities and node-centric method. But due to the limitation in the hardwares back then, the company stopped updating the product. So the last update of the Examine3D was 1999. Now, after 20 years, not only because more powerful hardwares are in the market, but also we realize the industry needs to have a powerful tool to provide a fast elastic analysis when they are facing with huge mining geometries. And these are the main reasons that we are launching EX3. About the features of EX3, first of all, you can import a variety of formats, and you can do lots of repairs. For example, if there's a hole or if there's a gap in the model, you can do lots of repair before starting the simulation. We are also having an advanced surface meshing, so you're also able to redefine the mesh on the surface on the interest area. Staging is another feature we added, so you are able to define multiple materials in different stages. You can do excavation, you can do backfill. If you want, you can easily import a surface or create a surface and define it as a joint or fault in the model. Grouping is another cool feature that we added, and we will cover it later on in a demo section. And GPU acceleration also is another cool feature we included in the engine in order to accelerate the speed of calculation. I will also later on in the demo talk about it. Here you can see the differences between EX3 and Examine 3D in this table, we can see how many new features we have added already in EX3 in compared with the Examine 3D. We are having multiple material, we are having an advanced mesh surface mesh generator, geometry repair, you can define your joint, and so on. That we will cover it later on in the PowerPoint. For modeling in EX3, we are using boundary element method. In this technique, only boundaries of the geometry would be discretized. So if I want to compare boundary element with the finite element, as you can see in the picture, boundary element mesh is only assigned to the surface. However, in finite element, the whole domain would require a 3D mesh. Noting that in the engine, we are using the indirect boundary element, which provides the solution for an infinite elastic domain. In other words, we do not need to define any external. In the boundary element method, you only need to discretize the surface, and whatever around it would be assumed as the photon. So if I want, so quickly, if I compare it with the finite element, you can see how the time that you need to spend in order to discretize the model. Here is just surface, however, in finite element, you need to define the mesh all around the excavation, which requires more time. Also, in order to improve the speed and accuracy of the simulation, engine uses node-centric method. Instead of using the classic element-centric that they put the nodes in the element, we are putting the nodes on the corner of the element. It requires a more advanced numerical implementation, but we did it because it can reduce the size of storage on memory to 50%, which is a lot in the boundary element context. Also, we are using a special integration technique which resolves the singularities if you are having a bad geometry or bad shaped elements. So this type of integration can resolve most of these singularities. Also, for modeling the multiple material, for example, if you have two different zones and each of them have different properties, in order to solve it, we need to satisfy the continuity of traction because we have equilibrium at each point in the domain, and also by satisfying the continuity of displacement. So this surface should behave the same in both sides. If you want to know more about the mathematical background, I recommend you to have a look at our paper that we published last year, and also we presented it in ISRM in Brazil. About the modeling in EX3 and also the design philosophy, my colleague Owen, who was in charge of UI, is going to continue the presentation.
Hi, everyone, and thank you, Sina, for that introduction. As he mentioned, I'm going to be going briefly through modeling in EX3, how to construct models, what we were thinking with design, and show a couple of demos. So starting here with the design philosophy, we had sort of 4 key areas we were focusing on as we were designing EX3. The first main focus was on geometry creation and repair. We wanted to make it as intuitive and as quick as possible. We know that one of the key challenges with building models is how to get from real world data to a model that can be understood by our engine and computed. Our second main focus was on complete interoperability. We know that there's a lot of different software out there, a lot of different geometry types, as well as a lot of our own software. So we wanted to make sure that whatever format you had your data in or your models in, we would be able to read it into EX3 just fine. A major focus for sure was on rapid prototyping. This definitely has to do with the speed with which you can build your geometry and your model, but it also has to do with the speed of the engine, speed of viewing results, all of this put together so that you can, as quickly as possible, build your model, see results, and then continue to prototype, change up stope patterns, all of this to get the answer you're looking for as quickly as possible. And the last main focus was thorough results visualization. We wanted to make sure that once you had your data, you could see it in whatever form you were looking for as clearly as possible, so that you can understand exactly what you've accomplished. Moving on, I'm going to be talking about exactly how you build a model in EX3. So the first step is to actually build the geometry. You can create this from component pieces or import geometry and repair it and post-process it directly in the program. Once you have your geometry built and it's something you're happy with, you can define the number of stages required for modeling. So this can be mining steps, for example, for how you're going to do your excavations. The next step is to do what is called divide all. For those familiar with RS3, you'll know exactly what this does, but I'm going to talk in a little more detail about what exactly this is about, but it's a crucial part of every model you build in EX3. The next step is to define your materials and to assign properties for every part. There's no actual meshing step required because EX3 will do the meshing in the background whenever there are pieces that can be meshed. So once you've reached this point, you can look at the mesh and do things like check the mesh quality, and then you can modify the mesh as you see fit. So there are global mesh settings that you can tweak or define things like refinement regions to gain a little bit more control. The last step that's required before compute is to define the field stress in the domain. As Sina mentioned before, it's the infinite domain and what field stress is being applied there. These are the steps to build your most basic EX3 model. These are the steps that have to be done for every EX3 model before you can compute, but there are some additional features that you can look at for some more advanced modeling, and we'll touch on a lot of those in the rest of the webinar. The last step after that obviously is to compute, and then from there you can view results. Looking at one of those additional things that will often be added to a model, when you're doing boundary element analysis, results are only calculated on the boundaries by default. So if you want to view results on the field outside of those boundaries, the areas that you want results on need to be defined in advance. So in order to do that, you can import point clouds, you can create query lines, or you can create planes and boxes that will be filled with points based on certain settings. When you're looking at creating a model to get from an empty project to a complete model, there's a bunch of different ways you can do this. You can obviously create the model fully in EX3, as we've talked about. You can import complete models from Examine 3D. You can import complete models from RS3, and you can actually import complete models as well from Map 3D. If you're looking to just import the geometry to start with, there's a variety of formats that we support, including OBJ, DXF, many more. This is the dialog that you would see when importing geometry, and I just want to emphasize that when you're importing from these files, if, for example, the pieces of your geometry are separated in the DXF, they'll be brought in as separate pieces, and you can select whatever pieces from that file you want to import. So if you're only interested in some subsection of that file, you can do that directly here. Once you have the geometry in, you want to look at repairing the geometry, filling gaps in the model, collapsing small pieces into larger ones, merging objects together, retriangulating surfaces, which can help smooth out the mesh, and forming closed volumes out of non-closed pieces. And in a further demo, we'll show how a lot of this works. One of the critical steps often is the geometry repair, which is done through a single unified geometry repair tool. You'll select geometry and then launch the geometry repair, and it will automatically detect any defects on that selected geometry. Once you have that, you can select what defects you're interested in repairing, and it will automatically repair whatever you've selected. The defects in the geometry it can detect are near-degenerate features, holes, near folding, self-intersections, and non-manifold, all of which I'm going to go through in a little more detail here. We're talking about near-degenerate features. What we're talking about is overly edgy features. This is any vertex that has many, many triangles connected to it, and the risk is that some of those triangles will be very, very thin, as you can see in the image down below. The risk of this is that it will end up creating sliver elements in the boundary element mesh, which can cause numerical problems and affect your results. When we're talking about holes, we're talking about any missing sections in a geometry surface. So the image down below is open-ended cylinder. We don't support open-ended geometries like that as volumes, and this will be interpreted as a surface. And the issue with that is material properties can only be applied to volumes. And when divide all is run with a geometry like this, this will actually be removed during the divide all process, because divide all only uses surfaces as cutting other volumes. So for this to be used as a tunnel geometry, this has to be fully closed. Near folding is another common problem. This is anytime you have two connected triangles that have a large difference in normal. This can happen sort of for two different cases. One is like the image down below, where you have the geometry folding back on itself. And the other is when you have inverted triangles within the surface mesh. The first problem can cause small volumes during the divide, which can also lead to very small elements. And the second can potentially cause inverted triangles in the boundary element mesh, which is a very serious problem and will cause many numeric issues in the engine. The second last one here is self-intersection. This is anytime two triangles on the surface mesh intersect. And this is just not a supported format for geometry to be in, so it'll cause strange behavior if you try and use that geometry in a variety of geometry operations. And the last that I have here is non-manifold. This is anytime more than two triangles are sharing a single edge. And this, again, is not a supported format for geometry, so it will result in strange behaviors during a variety of geometry operations. I'm going to now move on to the first demo here. Now this demo is going to be highlighting how to construct a geometry from a blank project all the way through to viewing results. So here you can see we've got just a blank project. I haven't done anything to this yet. This would be exactly as if you selected new project when you open EX3. And we're going to go to import geometry. I have a DXF file here that I'm going to be importing that contains some tunnels and stopes. We're going to open that up and we get the import geometry dialog. You can see the preview of it, and immediately it is pretty obvious that there are some problems with this geometry, so it is going to require some work. We're going to choose to import all the geometry in this case, so we're just going to select that and move on to the post-processing. Often it will be a good idea when here to do some simplification of the triangulation and look for defects. But in this example, there's a couple of changes I want to make to the geometry before we begin the repair. So I'm just going to import it as is. Once it's imported, I'm just going to expand the 3D view just to see the model a little more clearly. And what we're looking at here is a series of excavations inside of the host rock. So as Sina mentioned before, the host rock is an infinite domain around your model. So all of these geometries are marked as excavation with no material. So those are the excavated pieces, and everything that is not set as a volume is interpreted as host rock. For all of the geometry pieces, you can assign it both a role and a property. So all of these are currently assigned to no material as their property, and the role is set to excavation. The other two roles are geology and construction that we could assign right now. Geology is very similar to excavation, but it's interpreted a little bit differently for some geometric operations. And constructions are actually ignored by many operations, including divide all and meshing. So any construction pieces would not be meshed. In this model, the first thing we're going to notice is that there are these gaps in the geometry. So we have this single tunnel piece, but then there are these two pieces that have somehow become disconnected. So this will be a problem because, of course, this is interpreted as this piece being excavated, and then this gap here being host rock, and then the rest of this being excavated, which is obviously not what was intended. So this can be repaired quite simply. We're looking to connect these two faces. So the first thing I'm going to do is I'm going to select one face and then the other. Sorry, I'm just deselecting that piece there. So now I have the faces selected. We can go to Geometry, Surface Triangulation Tools, and we can just form a convex hull of these two selected faces. And if we look back at that section there, you can see that that has done a really nice job of repairing that gap. By default, the output of this convex hull operation will be construction geometry. So we're just going to change that back to excavation like everything else. And the applied property, which is currently host rock, we're going to change to no material. And now that is a piece of this tunnel, just like everything else. We're going to move over and do the same thing with the second gap very quickly. So just select one face and the other. Go geometry, convex hull. Now we can see that has repaired that hole very nicely. And we can just set this over to excavation. So now that our geometry is complete, we're going to look at repairing and see what sort of issues exist within what we have imported. So to do that, we are going to select everything because we want to repair the whole model rather than repairing some sub pieces, and move to the repair tool. When this is opened, it will search the model for defects. And you can see that it has actually found quite a few. A lot of these are near folding on the central tunnel here. The reason for this is there's a lot of inverted elements in the surface mesh that was originally brought in. A lot of these steps that we're taking, keep in mind, these would not be necessary if there weren't problems with the geometry. If this was a clean geometry we were bringing in, we could proceed a lot more quickly, but because of the issues, we have to first look to repair them. So we're going to deselect the near-degenerate features because they're not very serious on this geometry, and a lot of them will actually get resolved quite nicely by divide all. So we're looking only at the holes, the near folding, the self-intersections, and there aren't actually any non-manifold pieces on this geometry. When we hit repair, it's going to go through the defects that we've requested to have fixed, and it's going to try to automatically resolve them. This is an iterative process, so it will repair any defects, and then it will automatically search for new ones, as you just saw it's doing there. So now that it's resolved, we can see that it's gone searching for new defects, and all of the defects we're interested in have been repaired, which is very great. So when we close this now, you can see that some of that weird triangulation you were seeing on this central tunnel is now gone. This is because those inverted triangles are now gone, and so this is being recognized as smooth pieces and not showing quite as many edges. The next thing we're going to be doing is we're going to be looking at the actual triangulation of this geometry. So I'm going to increase the opacity of this and turn on show edges. So this shows the actual triangulation of the surface mesh of our geometry. And you can see that there are these very high density pieces here. So this is creating a lot of additional computational load. This density of triangulation is not really necessary for this sort of geometry. So we're just going to select these and look at how to simplify the triangulation. So we can go here, click Simplify Triangulation in the Surface Triangulation Tools. We're going to move to the Custom, and there's this by percentage option, and we are going to set this to 25%, which would reduce the density of the triangles by about 4 times. If we look at the preview of this, you can see that this is still a little bit more triangulated than it probably needs to be, but it's significantly improved, and the shape of the geometry is completely preserved. So this is a great first step. Divide all will also help with this issue, so we're just going to leave it there. This helps to reduce the computational load on the divide all process, and divide all will sort of take it the rest of the way to make the triangulation a lot more uniform. So with that, we are going to move on to the actual divide all. As I said, this is a central step for any modeling in EX3. So I'm just going to work with the default quality settings. We're going to hit OK. And as this is running, I'll just sort of describe briefly what exactly divide all is doing. This takes all the pieces of geometry that you've constructed and it forms them into distinct volumetric pieces. So if, for example, you had 2 volumes that had some overlap, instead of resulting in 2 volumes, it would result in 3, where you had the 2 pieces and then the overlap as a separate geometry. And this is critical for things like material assignments because it removes any ambiguity. So if those 2 volumes were assigned different materials, then what should that overlap be assigned to? Well, now that is a separate piece, so you can assign that overlap separately from the 2 separate pieces. So this has to be done for every model just so that you end up with those distinct volumes that we can interpret correctly. This is a bit of a slower divide than some other models, and that's because the geometry was actually quite messy, and there are a lot of what we call near intersections where pieces are very, very close to each other. This makes it a fair bit harder for divide all to resolve, and it has to do a few more iterations to check for things. That simplification of triangulation will help with the performance of divide all because it reduces the triangles it has to look through quite significantly. And in the end, the divide all will have new triangulation for the surfaces. So you'll see how much, once this resolves, it has actually improved the triangulation of that high dense region that we were looking at before. So it should just be wrapping up here, and then we'll take a look at the model state from there. It's the final steps here, and there we go. So I'm just going to once again increase the opacity, and you can see the difference now on this region that we were looking at before. It's very evenly triangulated with the rest of the model. There's many, like as you can see, through the rest of the model, the triangulation is now very, very consistent on the surface. So we are going to now turn off that showing all edges, so we're not looking at the surface mesh anymore. And there's now one more step I want to do to clean up this geometry, and that's to look at collapsing small volumes. We can go into geometry, repair, collapse small volumes. Now, there's many ways you can filter out what exactly is defined as a small volume, but in this model, the recommended setting works quite well. So we are going to look at, just quickly do an inspection of the pieces it's selected. The goal of this really is just to simplify the modeling process. So right now we have a lot of pieces, as you can see here, that are very small. They clearly don't have much impact on the model. They're not meaningful for staging. So there's no point in keeping these as separate pieces. Great example is these tunnel pieces that we've now repaired. Really, we want these collapsed into the surrounding tunnel because they're not meaningful for staging in any way. But one example of a piece we don't necessarily want to collapse is this piece here at the bottom of the stope. This might be quite valuable for stope staging later if we want this to be a particular mining step. So in this case, I'm just going to deselect that so it doesn't participate in the collapse. So now that that's done, I'm just going to hit collapse here. It'll take a second, and then there we go. And now we can take a look at what's been done. So if we look at this tunnel here, you can see this is now one single connected piece, which is very nice. That's really what we're looking for. And then this stope piece, which we deselected, this is still its own separate piece. So if we were looking to stage that, it'd be no problem to do so. Now that we have our geometry settled, I'm going to move on to the mesh. Now you can see that the mesh has already been constructed. Like I said, this happens in the background automatically when the pieces are complete. So in this case, looking at this mesh, it's a little bit sparse. I think it should be a bit denser for this model. So we're going to go quickly into the mesh settings. And you can see there's this mesh density option. We could change this to medium high. And what this actually affects is these advanced parameters. So if you're looking for a particular mesh setting or pattern to the mesh, you can play around with these advanced settings. And you can see, for example, when we go to medium, this is affecting the element resolutions. In this case, I think this is good enough for this model. So we're just going to move on with the medium settings and hit OK here. So you can see how in the background the mesh is now being constructed, and once it's available we can see it in the view. Now you can see that this is a fair bit denser than the previous mesh. It could probably be a little bit denser for this model, but for the sake of this demo I'm just going to leave it there and move on. Normally the next step would be to define your field points and your loading, but for this model we're just going to stick with the defaults because these will be covered in a later demo, and we're just going to move directly onto the compute. When we hit the compute button, it will save the work that we've done, which does take a little bit of time because there's a fair amount of information to copy. And then it will move on to launching the engine in a second here. It's a very small model, 10,000, so this will be a fairly quick compute. And the surface stress is there. And now that that's done, you can see the results on the surface of our geometry. In this case, you will notice that a lot of the results are biased towards the lower end of our contour range. Now, what's happened in this model, and this can happen sometimes, is there are a couple of nodes that have very high values relative to the rest of the model. And the contour range by default is always going to be set so that it covers all nodes. But in this case, it makes the results a little bit harder to interpret. So we can look at this new tool called the density histogram. When we toggle this, you can actually see how many nodes are having each value inside the contour range. And there's practically nothing at the higher end. So we can just adjust this slider up so that it gets closer to the lower end, and we can see the effect of that on the contours of the model. And now this is a much clearer view of what's happening, and we can accept this and now continue to work with the results with this new adjusted range. With that, I'm just going to switch back to the presentation here, and we're going to take a quick look at some example results for this model. So this is comparing Examine 3 and RS3. These are the total displacements. You can see the contour ranges are identical on the right side there. The contours themselves are very, very similar. If we look at the sigma 1 values, again, contour ranges are the same and the results are nearly identical. I'm now going to move on to a second short demo that's just going to show some of the imports that we have. We're going to be highlighting the importing of a Map3D file. We're going to be showing a little bit of the new grouping of geometry that you can do, as well as just a little bit of staging. So I'm going to move back now to our copy of EX3. And from this file, we're just going to hit import Map3D file. And this will allow you to import any .imp file. When we hit open, this will open it as a new project. And what it's going to import now is the geometries from Map3D, the grouping of the geometries in Map3D, and the mining steps. As you can see, mining steps 1 through 12, as well as the material properties and their staging. So this is just wrapping up the final steps of that import process now in order to convert their geometries into a format that we can work with. All right, and as that completes, we can see the geometry come into focus here. I'm just once again going to switch to the 3D view just to make it a little bit clearer. And we're going to just hide this surface for now because it obscures a lot of the model. So looking at the rest of the geometry here, you can see what we've imported. And for anyone who's familiar with Rocscience software, I'm sure you'll immediately notice that this looks quite a bit different from our normal 3D look. The reason for this, again, is because it's using the new geometry grouping option. So this has imported all of the groups that were used by the model in Map3D originally. So we can take a look now at the group dialog, and we can see all the groups that have been brought in. So these are all the groups as they were defined in Map3D. Each group has assigned to it a name, a color, and some transparency options. We wanted to make it so that the groups gave you as much flexibility for the visualization of your model as possible. So just as an example, we could take this ramp group and we could change it to purple color, and we could get rid of the group setting transparency. What that does is now, as you can see, this group is a different color and it's taking the transparency from the global options. So if we adjust these, you can see the effect now on that set of geometry. The reason why this was done was, again, just give you the flexibility, and also because sometimes it is quite useful to have one geometry that is always quite visual, even if the rest of the model is fairly transparent. The other great advantage of grouping is the ability to affect selection. So if we actually go over to the groups tree in the visibility tree, you can see now the same groups listed out here, and underneath each group is the geometries that it affects, or that are included in that group. And the great thing about this is now we can use this as a selection tool. So if I want to select everything in this group, or this group, or this group, I can do so with one click. So this means any feature that uses selection, if you want to affect the entire group, such as for translation or a repair, you can do that. And also, this is great for staging of material properties, because now you can select an entire group and affect their applied property. The one last thing I want to highlight is that with EX3, you can always switch between this new grouping visualization and the old material visualization. So if we're looking here now, I'm just once again going to adjust the opacity. This is the material assignments of the model. So we can switch back and forth between that grouping view and the material view whenever we want. And in this example, what you have is host rock assigned to all of these different tunnels, and then the ore body behind it. And we can look at the import job that is done for the staging of the materials. And as we step through the mining steps, more and more of the model is progressively excavated until we reach the final step where the whole model is excavated. So with that, I am now going to switch back over to my colleague Sina, and he's going to finish the presentation with a couple more demos.
Thank you so much, Owen. So I'm going to continue the presentation with two more demos. In the first demo, I want to show you how you can import the Examine 3D file. If you were one of our old customers and you have some files and you want to import them, how you can do it, how to calculate the results, how we can use the advantage of GPU acceleration, and also viewing the results in the field point and showing ISO surfaces. So to import the geometry, easily you can just go through the file, import and import the Examine 3D file. By importing that, you are bringing the geometry, not the mesh. Also the material properties, the field stresses in the domain, and also the location and orientation of the field point boxes would be preserved and will be imported into the EX3. So let me go back to into EX3 and show you how to do this. So simply click on File, Import Examine 3D file, and we pick the file. When you import it, a window will show up which tells you the object has been imported correctly. If there is any error or mistake in the file, you will be notified by the software. Meanwhile, you realize that when it imported, it did the divide all and meshing in the background. So you can see how the EX3 constructed the mesh for this model, which is different with the mesh implemented in the old Examine 3D. Also, you can see the three different field point boxes that has been defined. You can go, in order to check the geometry, you can go to Material tab, define material. You can see host rock has been defined with modular elasticity. In the SRAM tab, you can see hook brown has been used. It doesn't mean that we are doing the plastic analysis. EX3 is only doing elastic simulation. Based on the calculated stresses by elastic analysis, we are predicting the SRAM criteria all around the domain. So it's elastic simulation, not the plastic one. Also, if you go to the loading tab, and you can check the field stress, constant field stress has been used, sigma 1, sigma 2, sigma 3 are defined. In a diff direction, you can also change it to the vector, so you can define the orientation of sigma 1 and sigma 3, and obviously sigma 2 orientation would be perpendicular to them. And that's it for preparing the model for simulation. Before I click on compute, I want to emphasize, in this model, we are having almost 87,000 field points, which is a lot. So in order to accelerate the calculation, we can easily go to the file, preferences, and enable GPU acceleration. What it does is, because GPU has a lot of core, it assigns each core to one of the field points. And it does the calculation for that field point independent of the others. This way you can save a lot of time. So if I go to the compute tab, first I can save the model. Here, save it. And now I press compute. In the first stage, we assemble the matrix. After we assemble the matrix based on the field point defined in the host rock, we are solving the system of equation. We are using an iterative solution, GMRES, and you can see how fast it converged. After the convergence, we solve the results on the surface. While it's done, we are doing the calculation for the field point, if they are defined on the plane or even in the box. We can see how fast it's going. We almost have all the results in less than a minute, which is great for this example. And here we go. We have the results. But once again, we are only seeing the results on the surface. So if we want to see the results in the field point, let me turn off the results on the surface so we can see it better. To see the results on the field points, you need to define a contour plane in each of these field point boxes that you want. For example, if I define, if I click the first field point box, you can move to different boxes. You can define the orientation of the plane, XY direction, XZ direction, and so on. And by swiping this one, you can change the position of the plane. So if you want to see the results here, you simply click Add. If you move the plane to the other location, you again click Add, and we are preserving both of these planes. So if you click Cancel, you can easily see both of these field points, both of these planes inside the field point box. The other cool feature that we included in EX3 is ISO surfaces. So here is the icon. You can click on the ISO surface. These surfaces define a surface based on this inside each field point box that the user wants. So you can pick all of them or each of them. For example, here we picked the third one. So all the points on this surface, which are having the same value based on the data type that the user picks. For example, it can be sigma 1, sigma 2, mean stress, or total displacement, based on the value that user is inputting. Let's say 0.078. You can see the shape of the surface has been changed. So if I want to make it more obvious, let me click the surface and increase the transparency. You can see all the points on this surface right now are having the same value. In order to have a comparison with or other 3D softwares, we did an analysis in order to find the stress distribution in this region. So I'm just going to go back to the PowerPoint to show you the comparison of the results. Here you can see the results, the distribution of sigma 1 in EX3, in RST, and in Examine 3D. As you can see, in all of them, the hotspots has been captured correctly. Noting that in EX3, it took less than a minute, as you saw, but in Examine 3D, it took more than 11 minutes. The last demo that I want to talk about very quickly is about definition of multiple stages, how you can define multiple material and do excavation in several stages, and also defining the field point box. So I go back to the software again, and I pre-made this model in order to save time, and I simply open it. So what we have here is an ore with 2 different materials and 4 drifts. So if I go again to the material tab, you can see 4 different material are defined. You can increase them if in your model you have more than just 4 materials, as much as you want. And also in the project setting, you can control number of stages. So here in this example, we have 9 stages. You can increase them, or you can even change the name of each stage if you want to manage your file much easier. So what we are doing in this example, in the initial stage, we are just assigning the material properties. In the second stage, we are excavating the drifts. And the second stage, we are excavating the ore. So once we excavate, in the next stage, we want to backfill. Again, excavate more zones in the ore, and then backfill them, and so on. So after assigning each material, each properties to each zone, the model is ready to be, we are able to do the divide all. So we click on that. It can be done very fast. And now if I go to the mesh tab, you can see the mesh that constructed for the geometry. The last thing I want to mention is about the loading, which is very important. By default, we are having the constant field stress, which is 10 in each direction for each of the material. But we know that for the backfill, we do not want to add any pressure to the surrounding area of the backfill area. So we have to modify this stress for the backfill material. So if we want to do that, as you can see in a host rock in an advanced tab, if I click on each of material, by default it's 10, the same value. But for the backfill, you can simply just modify that with any number you want. So in this case, we have to assign 0 for the backfill material and then press OK. In order to see the results, you need to define the field point box. So we go to the field point tab and add field point box. You can easily change the size and also the location of the field point box. You can move it to your interest zone. For example, in this example, because we are doing excavations and backfills in this area, so I'm just reducing the size of the field point box. And then you can define number of grids on each side of this box. For example, 30 by 30 by 30. Press OK, and you can see them. If you want to see the distribution of them, once again, click on the field point box and activate the grid line. You can see how dense are the field points. And if you want to change the orientation of that, depict the box, go to the geometry tab, and then transform. So here you define the axis. It's about the Z axis, which is the desired direction. And then we change the orientation. You can preview that by pressing that preview button and then OK. So right now the field point box is aligned with the direction of the board. So we did the analysis here. It took, because it's 9 stages, it took about 3 minutes. So I did the calculation in advance and I'm just going to show you the results. In the first, the first one is the results after excavation, which happened in the stage 2. And then in the stage 5, as you can see here, because we assigned a 0 stress for the backfill zone, we are having 0 stress. And also you can see the results at the end, where we have most of the deformation. And that's it as a demo. I'm pleased to announce that we are having an upcoming webinar for EX3. This the current webinar was mostly for introducing the software, but on May 20th, we are going to hold another webinar using EX3 for underground mining application, which starts at 1 p.m. So if you want to attend, please register for that one. At the end, I just want to thank everyone who participated in this webinar. We hope you find it helpful. If you are interested to use the software, please send us an email. We will send you a link for the trial version. If you have any suggestion or you want to include any particular feature, please let us know. We would be more than happy to help you. Finally, on behalf of Rocscience, I wish you have a wonderful day and stay safe. Thank you.